I'm going to tell you about classical simulation of peaked shallow quantum circuits. This is joint work with Sergey Bravi and David Gossett. This talk is about classical simulation, which involves designing and analyzing classical algorithms for simulating quantum computation. We begin by familiarizing ourselves with the core notations that will be used throughout this talk. We let n denote the number of qubits, which mathematically is just a positive integer. For every length n binary string x, we use ket x to denote the x standard basis vector, where the entries of the vector are indexed by the set of all n-bit strings. So ket x is a 2 to the n dimensional one-hot vector. We let u denote an n-qubit quantum circuit, which can be represented by a 2 to the n by a 2 to the n complex matrix. We use ket psi to denote the result of multiplying the matrix U to the first standard basis vector, which just returns the first column of U, and that's it. And since psi is a unit vector, it induces a probability distribution P over the set of all n-bit strings, where the probability of observing an outcome X is given by the squared absolute value of the X entry of the vector psi. So far, syntactically, right, everything can be stated in terms of just linear algebra. But one reason why quantum computing differs from just linear algebra is because we're mostly interested in quantum circuits that possess some crucial locality structures. Here in the circuit diagram, every horizontal line represents one qubit, and each rectangle is a gate that acts on 2 qubits at a time. Mathematically, a quantum circuit U composed of m gates is the product of um through u1, where each ui is the tensor product of 2 by 2 identity matrices and a 2-qubit gate, or a 4 by 4 unitary matrix vi. Here, although each ui is a 2 to the n by 2 to the n matrix, it is completely specified by the 4 by 4 unitary matrix vi, plus some bookkeeping information about which 2 qubits the gate will be applied to. Therefore, the total number of parameters needed to specify the whole circuit U is only linear in the number of gates m. Without loss of generality, the input-output behavior of a perfect quantum computer can be described as follows. An input and n-qubit quantum circuit U specified by a list of 2-qubit gates, right, including the information about which qubits to apply each gate to, a perfect quantum computer will output an n-bit string sampled from the output distribution P. Then, unsurprisingly, one natural goal for classical simulation is to replicate the input-output behavior of the quantum computer, right? For simulated sampling, the goal is to have a classical computer sampling from approximately the same distribution, hence matching the capability of a fault-tolerant quantum computer. For a second natural classical simulation task, the goal is to estimate the probability of observing a certain string x. Say we have a classical simulation algorithm A that on input U can estimate the probability of observing all zeros. Then the same algorithm can be used to estimate quantities of this form for some other circuit of interest M. Here, U dagger is the inverse of U, and this works by the fact that U dagger MU is a proper quantum circuit. Why do we care about the classical simulation of quantum circuits? It better be the case that we cannot efficiently classically simulate an arbitrary quantum circuit, right? We can only hope to efficiently simulate special families of quantum circuits which satisfy some special properties. Here, I want to convince you that it is an interesting question to ask which properties are sufficient for admitting efficient classical simulation, for at least 2 reasons. Firstly, suppose we prove a theorem of the form: if a family of quantum circuits satisfies some property X, then that family of circuits can be efficiently classically simulated. Now, just taking the logical contrapositive, we get a statement that says, if a family of quantum circuits demonstrate quantum advantage, then those circuits cannot satisfy the property X. Therefore, classical simulation identifies necessary conditions for quantum advantage. In our work, we give classical simulation algorithms for peaked shallow quantum circuits. Right? A second reason why classical simulation can be interesting is because algorithms usually come about from a better understanding of the structure of the circuits satisfying the property X. And this is certainly the case for our work. Okay, what is a peaked shallow circuit? We say a quantum circuit U is shallow if its circuit depth is a constant independent of the number of qubits. Circuit depth is the number of layers of 2-qubit gates in the circuit. In this example, the circuit has depth 3. We say U is peaked if its maximum output probability is at least inverse polynomially large. What's special about peak circuits? Well, suppose you run the circuit U on the quantum computer polynomially many times to collect polynomially many samples. Then you would expect to see a collision, which means observing the same string more than once, if and only if the circuit U is peaked. Because of this collision property, Aronson has recently proposed peaked random circuit sampling for tackling the efficient verifiability issue of random circuit sampling experiments. How about peaked shallow circuits? I claim that the quantum part of many near-term quantum algorithms involves estimating the amplitudes of peaked shallow circuits. Why? Many near-term quantum algorithms use a quantum computer to estimate the expected value of a tensor product, a Hermitian unitary, at the output of a shallow circuit through Monte Carlo sampling, ideally to within inverse polynomial additive error. First, notice that if the magnitude of the value to be estimated is much smaller than 1 over poly n, then the task becomes trivial because simply outputting 0 satisfies the inverse polynomial additive error accuracy requirement. However, if this value is at least 1 over poly n, then the shallow circuit U dagger MU is peaked according to our definition of peakness. U dagger MU is still shallow because U is shallow, and the depth of U dagger MU is at most double the depth of U. Therefore, this task reduces to estimating the 0,0 amplitude of the shallow circuit U dagger MU. And it is non-trivial if and only if U dagger MU is peaked. Next, I'm going to state our main results. We give classical sampling algorithms that do the following. An input an n-qubit shallow circuit U and an error tolerance epsilon at least 1 over poly n, the algorithms either output an n-bit string X drawn from some distribution P prime, that's epsilon close to P in 1 norm, or throws a circuit is not peaked error. The runtimes of our algorithms depend on the geometric locality of the input circuit. For 2D peak shallow circuits, we give a polynomial time algorithm. In a 2D quantum circuit, we have n qubits living on the vertices of a root n by root n grid. 2-qubit gates can only be applied to neighboring qubits either horizontally or vertically, like this. For general unrestricted peak shallow circuits, we give a quasi-polynomial time algorithm, that is n to the O log n time. What's in between polynomial and quasi-polynomial? For 3D and higher constant spatial dimension, our algorithm runs in almost polynomial time. In fact, n to the O log n time. As a corollary, we obtain algorithms for the second simulation task of output probability estimation. Right? On input, a shallow circuit U, a target string X, and an inverse polynomial epsilon, our algorithms output a number P that approximates P of X to within epsilon additive error. It's important to know that for this task, we don't need to assume the input circuit is peaked because the problem is trivial if it's not, and simply outputting 0 suffices. Right? Crucially, the algorithm knows when to just output 0. Right? Basically, it's when the sampling algorithms throw the circuit is not peaked error. The time complexities of our output probability estimation algorithms are the same as the corresponding ones for sampling. For the unrestricted architecture, our algorithm represents an exponential improvement in runtime over prior work. For 3D and higher, our algorithm has an exponentially smaller exponent compared to the previous state-of-the-art. In the remainder of this talk, I'm going to describe how our general architecture algorithm works. Okay, the line count of an output qubit I is the set of all input qubits that are causally connected to the qubit I by the circuit. In the example here, the line count of the second output qubit consists of the top 4 input qubits. The key property of line cones of shallow circuits is that if 2 output qubits I and j have disjoint line cones, then I and j have independent marginal output probabilities. The joint marginal distribution of I and j is the product of the marginal for I and the marginal for j. For a shallow depth D circuit, where D is a constant, no matter how the gates are arranged, the expansion in the light cone size is at most 2 to the D, which is still just a constant. Right? From this, we can show that for a shallow circuit, any output qubit is correlated with only a constant number of other output qubits. In other words, the distribution P has a limited dependency structure. So to gain some intuition about the output distribution of a peak shallow circuit, it is instructive to consider a toy model where P is a product distribution and the peak is the odd-zero string. Firstly, we claim that for this toy model, the expected Hamming weight of a string X drawn from P is at most log n. And here's a one-line proof. I'll give you a few seconds to stare at this proof. Right, this shows that we would expect to see at least n minus log n zeros, which means the expected Hamming weight, or the number of ones, right, is at most log n. Now, it is straightforward to apply a multiplicative Chernoff bound to strengthen the expectation bound to a concentration bound. It turns out that an analogous Hamming weight concentration property holds for the output distribution of peak shallow circuits. We proved that for a peak shallow circuit where each output bit is locally biased towards 0, the output distribution is concentrated on strings of Hamming weight at most log n. The total probability mass occupied by higher Hamming weight strings is at most inverse polynomial. This is the main structural property of peak shallow circuits that we proved, and it naturally leads to our classical simulation algorithm. For comparison, it is known that the output distribution of a shallow but not necessarily peaked circuit is concentrated on a Hamming ball of radius square root of n. Okay, log n Hamming weight concentration means that the output state psi mostly lives in the n to the log n dimensional low Hamming weight subspace. It's n to the log n dimensional because the total number of strings of Hamming weight at most log n is at most n to the log n. Next, we show that the output state of a peak shallow circuit is well approximated by a state phi supported on the low Hamming weight subspace. The overlap between phi and psi is at least 1 minus epsilon. Our algorithm constructs phi explicitly as follows. We consider this Hermitian matrix H, which is defined so that psi is the unique eigenvector of H corresponding to the largest eigenvalue 1. Every other eigenvector of H corresponds to a smaller eigenvalue. We consider the restriction of H onto the low Hamming weight subspace, which is just an n to the log n by n to the log n submatrix of H in the standard basis. We show that a largest eigenvector of this much smaller matrix G is the approximation we want. So here's the algorithm. Step 1, construct G as a sparse matrix by computing all its matrix elements. Step 2, compute the largest eigenvalue of G with a corresponding eigenvector. If lambda 1 of G is not close enough to 1, then throw the circuit is not peaked there. Otherwise, output the eigenvector as the approximation to psi. I'm going to end the talk here by leaving up some open problems. Thank you for your attention.